Hello and welcome. So this is from Fitness Coaching. Now this particular video is particularly useful for students who are preparing for FRM, and we are going to cover two of the central moments, which is skewness and kurtosis. And I'm going to take you through how we can construct graphs on Excel, as well as the the how do we validate the measures of skewness and kurtosis statistically, as well as using the formulae. And if there are any methods which can be provided, we will be validating those as well. So I'm going to start by sharing my screen here. So let's say this is the marks for students who have appeared in term one. Now, mind you, we are going to use these formulae for skewness and kurtosis. Now, for term one, these are the marks, right? Now, let's see, first of all, what kind of uh, what kind of data or the distribution it is. Is it symmetrical perfectly, which is typically what happens in a normal distribution? Or is it positively skewed, which is called as the right skew? Or is it negatively skewed, which is called as the left skew? Okay. So for doing that, the first thing we will need to do is basically, so I'm going to go to data. There is something called as descriptive statistics. So I'm going to take descriptive statistics here. And I'm going to take the input range, which will basically give me all the statistics about this distribution, the mean, median, mode, skewness, kurtosis, everything. Now, if I take the input range as the marks here, obviously the data is grouped in columns, and the output range I'll put somewhere here, and I'll tick the summary statistics and press OK. The moment I do that, I will get the output. I'll get the summary statistics. What I'm going to do next is I'm going to show you the characteristics of this distribution. Now, if you look here, the mean is greater than the median, and the median is greater than the mode. You can see that the mean is greater than the median, and that is greater than the mode, which basically suggests that it is a positively skewed distribution, which you can also see validate by the skewness measure that you get here. This is positively skewed, right? Now let's try to construct a graph. For doing that, I will need to create a bin, because you need to put the bin values and the input values when you want to construct a graph. Before that, when you want to construct a histogram rather. So what we will do, we will take plus minus 3 standard deviations from the mean. So what I will do now is I will do is equal to mean minus 3 times the standard deviation. Next one, I want mean minus 2 times the standard deviation. So what I can do, I can just add one standard deviation and I will get mean minus 2. And I just need to freeze the standard deviation. And now next one will be mean minus 1 standard deviation. This will be the mean. And then plus 1, 2, 3. So now we have data which starts from the mean minus 3 standard deviations, mean minus 2 standard deviations, mean minus 1 standard deviation, the mean, which you can see is the same as here, mean plus 1 standard, mean plus 2 standards, mean plus 3 standard deviations. Now this is what we have got here, right? So I am going to now use this data to construct a histogram. So again, I go to the data analysis pack, and this is the histogram. And now I will take the input range and the bin range and the output range. So the input range very clearly is the mark. So I'm going to put that in the input range. The bin range is also given here. And the output range I can probably keep here. And I'm going to press OK. Now, the moment I do that, I will get a histogram. Now, I want to make sense of this histogram. So typically, I'm going to just insert a bubble scatter. And this is my skew. Now you can look here. Positively skewed means the tail will be longer. This graph may not look as appropriate. So probably if you take it from here, I think that might be better. Yes. So now if you look here, it's clear that the left tail is extremely short. The right one is long. So this is definitely skewed to the right. So this is a positively skewed distribution. And here you will see that the scores towards lower side of scale, okay, please hear what I'm saying carefully. The scores towards the lower side of the scale are more. Okay, so there is a tilt towards of the scores which are falling towards the lower side of the scale, and very few scores towards the higher side of the scale, and that's why it results in a positive skew. You can look at the marks also. The mean is 39, so you'll see most of the observations are below 39. Only some of the observations are above 39. So more scores fall towards the lower side of the scale, and very few high scores. So this is the skewness chart I can which you can clearly see. Now, how can we validate the skewness? We will be using this formula. So first I need the uh, deviations cubed. So I will straight away capture the deviations cubed, which is xi minus x bar, which is the mean, to the power of 3. All I need to do now is my mean, because that is a static observation, and drag it to the bottom. Now we are ready to calculate the skewness. So if you look at the FRM textbooks, what they say is skewness is nothing but a sum of xi minus x bar cubed. But please remember, divided by, now in this case, there are 16 observations. Okay, we can actually see that 16 observations. So this is the average of that, and that divided by standard deviation cubed to the power of 3. Now, if you do that, you will get a value of 1.06. Now, please remember, this is an estimate. That's why you will see this figure does not match this figure of skewness. But it's okay. It will still give you a fairly close estimate to what the skewness is. Now, if you want to really validate the skewness, you will have to adjust the bias in the data, and that we will do by doing n by n minus 1 into n minus 2. So for the bias factor, I'm going to do is equal to n, which is 16, divided by n minus 1, which is 15, into n minus 2, which is 14. Now, this is my bias factor. And what I am going to do now is I am going to multiply this value so this is sigma xi minus x bar, but here I will not divide by 16, okay? Because the reason for not dividing by 16 is what? Because here we are anyways doing a bias of n by n minus 1 into n minus 2 separately. So there is no need of doing 1 by 16. See, 1 by 16 will also be close to that, right? You see it's 0.06, this is 0.07. But statistically, this bias is more accurate. So I am going to now multiply this number with this, and I will get my skewness figure. And now we can see the skewness exactly matches the number that you have obtained on the chart. Without any problem, this is the skewness. Similarly, we can also validate the kurtosis. Now, what do you mean by kurtosis? Kurtosis basically measures the shape of the distribution. Okay, so basically it tells you the probability of the I mean, what probabilities rather reside in the tails of the distribution relative to the total population. That is what kurtosis measures. So higher the kurtosis means higher the percentage in the tail. So that's why these are also called as fat-tailed distributions. Now, there are three types of kurtosis. You have mesokurtic, which is exactly how it should be. Then you have platykurtic and leptokurtic. Leptokurtic is the taller one, and platykurtic is the flatter one. And we will see how the probabilities, or rather how the kurtosis values can be obtained now. So for the kurtosis, we will follow this formula. This is the bias. But before that, I am going to take the square deviations to the power of 4. And that will be simply xi minus x bar, each individual distribution minus the mean to the power of 4, and drag this to the right. Sorry, freeze it and drag it to the bottom. And now I will get the kurtosis value, which will be, first we will have to calculate the bias factor. So let's do that. So summation of xi minus x bar to the power of 4, that is in the numerator, and standard deviation to the power of 4 is in the denominator. And then there is this bias factor, which is n into n plus 1 divided by n minus 1 15 into n minus 2 14 into n minus 3 13. So that's how you get the bias factor. Now let's try and see what the kurtosis value comes out to be. So this comes out to be 55.63. And this 55.63, we'll have to divide, or rather multiply, with the adjustment bias. But now, up till now, the adjustment hasn't been completed. From this value that you obtained, we will have to reduce 3 times n minus 1 square. So that is 15 square. And then divide this by n minus 2, which is 14, into n minus 3, which is 30. That will complete your bias adjustment. So minus 3 times. Yes, so I just have to be careful of the bond mass here. And now if you look here, the value exactly matches what is given in your descriptive statistics. Can you see that figure, please, all of you? This is the figure, 1.83. So that's how you compute the kurtosis. So take the summation xi minus x bar to the power of 4 by standard deviation to the power of 4, multiply that with the bias, which is n into n plus 1 by n minus 1 into n minus 2 into n minus 3. And then from that value, we will reduce 3 times n minus 1 square divided by n minus 2 into n minus 3. And then that will be your kurtosis value. So now we come to the next part as to what is excess kurtosis. Okay. Now, excess kurtosis is very simple. If you want to see for mesocortic distributions, now typically we use a benchmark of 3. So the kurtosis value is approximately 3, then the excess kurtosis is 0. If the kurtosis value is more than 3, then the excess value or the excess kurtosis will be a positive value, and that happens in leptokurtic distributions, which are high peaked. And then you have the platykurtic, in which the kurtosis value is less than 3, and therefore excess kurtosis is negative, and that will happen in the platykurtic distributions. Mesocortic, obviously, the kurtosis value will be around 3, and therefore there will be no excess kurtosis. So these are the three different types of kurtosis: mesocortic distributions, leptokurtic distributions, and platykurtic distributions. So that was the idea of finding out kurtosis. Now let's compare this with the term 2 marks and see what happens in case of term 2. So for term 2, again, I have the data here. So I take this data and I'm going to put it here somewhere. And this I'm going to write as term 2. Okay. So now again, first step is to calculate or rather get your descriptive statistics of data analysis. Go to the descriptive statistics and press OK. Now here the ranges are going to move from term 1 to term 2. So we'll have to make sure that we update. So the input range now becomes your term 2 marks. And the output range, you can probably keep it here somewhere and press OK, and you will get your summary statistics. Now be very careful. Here you see the mean is less than the median, and obviously in this case the mode is the same, but generally in negative skew distributions, the mean will be less than the median, will be less than the mode. And here you will have higher, a lot of higher scores and very few low scores, right? So that is the main thing. So now what I'm going to do is I'm going to create a bin value the way I created here. So I'm just going to do it here, and I have to be careful that I do the referencing properly. So this is mean minus 3 standard deviations. Here I'll have to make the adjustment. So this plus 1 standard deviation, and then freeze it and drag it down, right? So this will be your bin values, and you can check this, and this value is the same the way I told you last time. So this is mean minus 3, mean minus 2, mean minus 1, mean plus 1, plus 2, plus 3. So we have got all values minus 3 standard deviations to plus 3 standard deviations. And now we are ready to populate the histogram. So I'm going to now populate the histogram, and let's see how it is. So the input range is basically your term 2 marks. The bin range is what you get here. And the output range will be somewhere here. And I press OK, and now I get my histogram. So now what I will do is I will construct a graph, insert a scatter, and now you will see a very different skew coming up. Now you see the difference between this and this. So here you have the tail, which is more pronounced. So this is a negative skew. Now, similarly, we can also measure the skewness and kurtosis here. Now, please remember, see, This is a negative skew distribution. You can see that the skewness is negative, and the kurtosis value is slightly lower than that of the first term marks. And we can again do the same calculations and get to the skewness and kurtosis measures simply by doing some adjustments to the formulae. And we have to be a little careful about the positions, and we will be able to get it. So here, if you look at xi minus x bar, so I'll have to change the position of x bar. So let's change this. X bar is this value. Yeah, E45, perfect. And I'll just freeze this and drag it down. And this is your numerator, denominator, which is the cube of the standard deviation. This gives you your bias. And now, sorry, this gives you the value. And now let's look at the, again, this is going to be the same. So for skewness, I think we have calculated it here. So this one is the value, summation of xi minus x bar cube to the power of 3. This is your standard deviation to the power of 3. If you divide, you get this value. And now this value we are going to multiply with the bias, which is the formula here, n by n minus 1 into n minus 2, so 16 by 15 into 14. And when we multiply both, we get the same value that you're getting here, 1.3396578. So the skewness part I have kept on this side, and the kurtosis part I have kept on this side. Again, here I will have to make the adjustments. I will have to take the x bar from here and freeze this and take it to the power of 4. So this is it. Here also standard deviation to the power of 4. Divide, you get this. And then n into n plus 1 by n minus 1 into n minus 2 into n minus 3. Multiply it. And with this number, just do minus of 3 into n minus 1 square divided by n minus 2 into n minus 3, and you will get the same value that you are getting here. Okay, we got the same values that we got here for skewness as for kurtosis. So just a summary or a quick recap, and very relevant for those who are studying FRM, because they have a clear chapter around skewness and kurtosis in the central readings, which is covered in reading number 13, and LO 13C, which talks about the population movements. This video could come in handy to be able to understand skewness and kurtosis. So we know now that where the skewness is 0, it's perfectly symmetrical. Positive skew, what it means. Negative skew, what does that mean? What are the 3 types of kurtosis? Kurtosis basically endorses the shape of the distribution, and it measures the probability that resides in the tails vis-a-vis the total. Higher the kurtosis, the more, you are moving towards fat-tailed distributions. It could be mesokurtic, where there is no excess value, leptokurtic, which has a positive excess value, and platykurtic, which has a negative excess value, taking a benchmark of kurtosis of 3. I hope you enjoyed the video. Thank you very much. Take care.